Okay, good. So for the first lecture of the afternoon session, Alex Iosevich is going to speak about discrete, continuous, and arithmetic aspects.
Thank you very much. It's an honor and a pleasure to be here. So one of the things I try to do is to make the lectures completely elementary. They assume virtually no background. Of course, whenever people say this, it's a lie to some extent, but we'll see how much. So the early lectures, the first two lectures, are going to be mostly in a discrete setting, but I'm going to begin with a continuous problem that kind of motivates things from my point of view. Jesus. Why is it always like this? Okay, no problem. All right. So one of the central problems in harmonic analysis is the restriction conjecture. And what it says is that if you take a Fourier transform of a function, restrict it to a sphere, then it satisfies a certain range of LP to LR inequalities. Okay, and this innocent-looking problem has tremendous impact on much of mathematics. It's related to geometric measure theory in the form of the Kakeya conjecture. It comes up all over the place in PDE, in the Schrödinger equation in particular. One could easily give a series of lectures just describing the impact of the restriction conjecture, never mind talking about the problem itself. Okay? And in spite of tremendous efforts by some of the greatest harmonic analysts, the problem is still open in higher dimensions. In 2 dimensions, various forms of it were proved by Zygmunt and by Pfefferman. Okay? So the first thing I would like to do is to give you a very straightforward and elementary perspective on the restriction conjecture from the standpoint of signal recovery. Now, signal recovery in this context should not be taken too seriously because the practical problem is, of course, finite. Nevertheless, it illustrates one of the simple but central ideas in these lectures. Okay? So suppose you have a compact set in RD, positive Lebesgue measure, and suppose that the Fourier transform is known except for the delta neighborhood of the sphere. And the question that we ask is, can we recover the indicator function of A exactly? Okay? By the way, another thing that I forgot to say in the beginning is please interrupt me anytime for any reason. If I don't cover everything I was planning to, the world is not going to end, at least not for that reason. Okay, so we write the indicator function of the set, and as an inverse Fourier transform of its Fourier transform. And then we split up the integral into the known frequencies, the ones not in the delta neighborhood of the sphere, plus the integral over the unknown frequencies. So that's 1 of x plus 2 of x. Okay? So the second integral is over the unknown frequencies. So since they're unknown, there's not much we can do except estimate the hell out of it and hope for the best. And that's exactly what we are going to do. Okay. And so, once again, known frequencies, unknown frequencies. So we apply Holder's inequality, followed by the restriction theorem, and we bound the second term over the unknown frequencies by the volume of the delta neighborhood of the sphere, times essentially the LR norm of the restriction operator. Why do I say essentially? There's a small amount of fudging here, but those who work in this problem know that it's not really fudging. Okay, where we thicken the sphere and then we divide by the volume. Okay, and I believe that any technique that's ever been devised for estimating the restriction operator applies to this approximate version. Okay? And by assumption, this is bounded by a constant times the volume of the delta neighborhood of the sphere times the LP norm of the function, which is just the measure of A raised to the power of 1 over P. Okay? So far, nothing revolutionary has happened. Okay, and nothing revolutionary is going to happen. So imagine that the right-hand side is bounded about by 1/2. Okay? Which amounts to saying that the measure of A is bounded above by a suitable constant times delta to the minus p, where what is p? P is the exponent afforded to us by the restriction conjecture.
Yeah, but Alex, I don't understand. You, in the restriction conjecture, there is just integral over the sphere of the Fourier transform. Here you have integral over the annulus.
Annulus divided by the volume of the annulus.
Why divided?
Well, because
nothing was divided. It was just integral over this.
sure, but it's the same thing. It's essentially the same thing because suppose you want to approximate the measure on the sphere, then you simply thicken the sphere by delta and you divide by the measure.
Arithmetic doesn't work.
It does?
It does.
Okay. So the Lebesgue measure on the sphere is essentially the limit.
Okay, I understand.
Yes, it's essentially the limit of you take the indicator function and you divide by the volume. All right, so once again, we bounded by a constant times the volume of the annulus times the measure of a raised to the power of 1 over p. And suppose that this is less than a half. If this is less than a half, then we can go back and apply the following, I'm sorry, I'm having trouble with this. And we can apply the following advanced algorithm. We can take the first integral, compute its modulus, and round up to 1 or down to 0. And this gives us an exact recovery because the error term, by assumption, is less than a half. Okay? So the point that I'm trying to make here is that if the measure of A is bounded by a suitable constant times delta to the minus P, okay, then we can achieve exact recovery. And what is P? P is the largest exponent so that the restriction conjecture works. Okay? By very elementary uncertainty principle considerations, and I'll talk about that more as the lectures go on, we can always take P equals 1. And this is also reflected in the fact that L1 restriction conjecture always holds by the triangle inequality. Okay? However, the larger the P, the less stringent is our recovery condition. And this is going to be one of the central themes in the lectures. Okay, please. There's a list of indices, P and R, for which the restriction conjecture holds.
But here in your application.
Here, you choose an R, which gives you the largest P.
Okay.
Okay.
And
So
can you explain why do we expect just this fat annulus not to be missing? Like, where does this come
Oh,
from?
no. So I gave you an immediate disclaimer that this is not meant to be understood from a practical point of view. I simply wanted to illustrate how a restriction conjecture comes in to play in these problems. Although, as it turns out, as I've learned in the past year, frequencies missing on the sphere even make sense in the applied context, but I'm going to talk about that later. Okay, problem fixed, yes?
Hopefully. You just sort of zoom out a little bit. And then hopefully it'll be okay.
Okay, I was just too stressed to make any intelligent decision. Okay, so as I mentioned, the restriction theorem always holds for P equals 1, but if we believe the restriction conjecture, which I do, right, then it holds for any P less than 2D over D plus 1. When D is large, this is asymptotically close to 2. So the gain is 1 over delta versus 1 over delta, almost 1 over delta squared. So this illustrates how in the presence of a restriction estimate, we get a better recovery condition. And so as I mentioned, from a practical point of view, these recovery problems are typically done in a discrete context. The reason I chose to go with the continuous case first is because I am a harmonic analyst, and this is how I think about these things. Okay? All right. So now let's go to the setting of finite signals. And here again, I'm slightly worried about putting half the audience to sleep because I'm literally going to prove everything. Okay, so f is a signal of finite length. So it's a function from Z and D to C, But when I started working on this, I learned that engineers insist on calling them signals. I have no objection. Okay. And suppose that the Fourier transform of f is transmitted. And here the Fourier transform is defined with an L2 normalization, namely to make Plancherel have constant 1. I used to use a different normalization, but my co-authors threatened to kill me. Okay. And so this is with respect to the character chi, where chi of t is e to the 2 pi I t over n. Okay? Now Fourier inversion says that we can recover the signal by using a Fourier inversion formula. So think of this as a game where I want to send you a signal f, but first I encode it as the discrete Fourier transform. I send it to you. If there's no interference of any kind, you receive the whole Fourier transform, and you learn Fourier inversion formula in school, so you invert it and you get the signal back. Okay? Of course, life is never this easy, otherwise we would be out of business. And so the basic question here is, can we recover f exactly from its discrete Fourier transform if the frequencies f hat of m, where m is in S, are unobserved or missing due to noise, interference, security, etc. I'm not going to pretend that I'm an applied mathematician. Okay? And for some S in Z and D. So the illustration that I gave you a few minutes ago is what happens with a continuous signal when the frequencies in a delta neighborhood of the sphere are missing. Okay? Okay. So the answer is yes. If f is supported in E, for example, in Z and D, and the size of E times the size of the missing frequencies is less than n to the d over 2, with the main tool being the Fourier uncertainty principle. Okay? And, okay, we'll get there. And, please.
Alex, too fast.
No, oh, no worries. I'm happy to slow down.
Too fast.
No worries. Absolutely. If I go too fast, I will have to write more slides. I mean, this,
Yeah.
I have to
What
write
if
more.
we have noise? I mean,
What?
from a practical perspective, you might have some noise.
Right, right. Now, it's not difficult to imagine why a signal would be missing. It's a different story of whether things happen in such a nice way, but that's a...
Well, like in practice, these work coefficients themselves will be measured in a noisy way, so you'll have some...
Right, right. These are extra complications, and I may get to that in later lectures. Okay.
Sorry, so is that strict inequality important?
This strict inequality is important, and you will see why.
I mean, otherwise, you get half, you don't know if it's 0 or 1.
Right, right, but yeah, but I will give you a concrete example, but it's exactly what he said. Okay, and all right, so as I promised, I'm going to prove everything. Whatever I don't prove, I'm going to give you exact references. So if you have a signal from Z and D to C, we're going to use the following formulas repeatedly. One is the Fourier inversion that I already mentioned, and here it holds with normalization n to the minus d over 2. And the other one is Plancherel, which holds with constant 1. Okay? And, okay, so let me describe a few simple calculations, because not everybody in this room has worked in this discrete setting. So let me just show you a few very quick discrete calculations just to get into the flow of things. Okay?
Sorry, just to check, so
Please.
to make the formulas easier to remember. So was it that the normalization is basically same for the inverse and the direct?
Yes,
Yeah, just
because that's the only way to make constant
Right.
1 in Plancherel. Right. It's much of my life I used a different normalization, but this is why I had to go through these notes 5 times to fish out.
Yeah, I
all
think
the
on the
discrepancies.
the first time you had the inversion, I think the
Yes,
normalization was missing.
normalization was, that's right. The first time normalization was, oh lordy, sorry. Okay, but now I'm making actual concrete calculations, so this will be better. Okay, so let me show you just a few quick calculations just to get a feel for these types of problems. So let's take a paraboloid. So xd is x1 squared all the way up to xd minus 1 squared. And let's compute its Fourier transform. So it's n to the minus d over 2, chi of minus y dot m prime, plus the so-called length of y times md, where the length is just a sum of squares. But one shouldn't laugh at the notion of length too much, because it's still invariant under the orthogonal group, so many of the properties carry over. Okay? And so suppose that md is 0 and m prime doesn't equal to 0, then by the orthogonality of characters, we simply get 0. Okay? Now, suppose that md doesn't equal to 0, and let's consider the case m prime is identically 0. Okay? So then we have n to the minus d over 2, summation of chi of minus md times this length of y, which is just a product of Gauss sums. So it's a product of sums of the form g of a times the summation over t in Zn of chi of at squared. So it's a classical Gauss sum. So let's go ahead and estimate the classical Gauss sum. If you're a harmonic analyst, you know that there are only 2 or 3 techniques in harmonic analysis, and the main one being TT star, right? Okay, so we take the modulus of the Gauss sum squared, okay? So we get summation of chi of a t squared minus s squared. Okay? When I teach undergraduate classes, I always tell the students that one of the most important techniques in mathematics is to realize that when you square an integral, it's the same as writing it twice with a different letter. And I'm not sure they believe me, but they will. Okay, so it's a summation of chi of a t squared minus s squared. Now just rotate by 45 degrees, and you have a summation of chi of a t s. Okay. Now just go on the level set, Ts equals u, summation over u of chi of au. And this is a summation of chi of au times n of u. So we converted the problem essentially to the Fourier transform of the function that counts the number of solutions of Ts equals u. Okay? Now, computing this function is not rocket science. So n of 0 is 2n minus 1. And if n doesn't equal to 0, you have n minus 1. Because once you fix t, s is determined. So the modulus of g of a squared is 2n minus 1 plus n minus 1 times the sum of non-zero characters. We absorb the 0 character. So we get capital N plus n minus 1 times the sum of all characters. And that sum, of course, is 0 by the orthogonality of characters. Okay? Life is good? Excellent. And which gives us capital N. And from this we conclude that the modulus of g of a is equal to square root of n. Note that we assume that n is prime. Okay? If n is not prime, then one never gets square root cancellation, and I'll say more about this later as needed. Okay? So going back to the paraboloid, if n is an odd prime, we see that the Fourier transform at 0 with md non being 0 is simply equal to capital N to the minus half. Okay, except that there is a small lie here. The modulus of this is n to the minus half. Okay? Which means that the modulus of the exponential sum also has to be taken. And if md is not 0 and m prime is also not identically 0, then we can complete the square and obtain the same bounds. Okay? I promise to give you complete proofs, but I think that completing the square in this company is probably not necessary. Okay? And so in other words, when md is not 0, the Fourier transform is equal to n to the minus a half. Okay? So I'm going to comment on that estimate in a moment in a more general setting, but let me also point out what happens in the case of the sphere. I really think it's an instructive example because in Euclidean space, estimating the Fourier transform of the measure in the sphere is essentially calculus 3 exercise. Okay? In finite fields, not so much, so let me tell you why. So suppose that m is not identically 0, then as usual we synthesize the delta function on the sphere. We put in chi of s norm x minus 1, and if you sum over all S, you get 0 unless norm x equals 1. Now, I excluded S equals 0, because if M doesn't equal to 0 and S does, then you simply get 0 for this expression by the orthogonality of characters. Okay? So we keep going, so we complete the square. So I just told you that I didn't need to complete the square in this company, but I did anyways. Okay? So we complete the square over here, and we change variables, and we arrive, wait, what happened? Okay? And we arrive at the following expression. So it's n to the minus d over 2 minus 1. Then you have a summation over s not equal to 0, and a summation over x. And here we see chi of s length of x. So this is a product of the Gauss sums that we just discussed. Okay? So if we plug in the bounds for the Gauss sums, we get n to the minus 1 times the summation of gamma to the power of d of s. Here, gamma has modulus 1, it's unimodular, and chi of minus s minus length of m over 4s. Okay? And this innocent-looking expression is called a Kloosterman-Sallee sum, and the estimation of this sum, I think it would not be an exaggeration to say that it's one of the greatest accomplishments of 20th century mathematics. It cannot be done by integration by parts in 2 lines the way you can do it with a sphere. Okay? And so it is known that the modulus of this sum is bounded by 2 times square root of n. The proof is quite sophisticated. Even after Stepanov came up with a quote-unquote elementary proof, it's still at 25 pages of brutal calculations. Okay? All right, so in conclusion, once again, the Fourier transform of an indicator function of the sphere on a non-zero vector is bounded by a constant times n to the minus half. In this case, this constant may be taken to be 2. Okay? So one issue here is we took n to be prime, which raises, I think, a very interesting question of what happens in general. And I think that this could be a subject matter for a whole different lecture series. But let me say a few things in passing. Okay? So in both cases, what we get is a manifestation of a so-called square root law, where an exponential sum behaves, where the summands of the exponential sum behave as if they were independent random variables. Okay? And so what we get here is that the Fourier transform is bounded by a constant. N to the minus d over 2 comes from normalization, and then we have the number of summands raised to the power of 1/2. That's the meaning of the square root law. Okay? And it is very easy to see that you cannot do better than the square root law because you would violate Plancherel. Okay? In other words, if you literally took something better than the square root law, you plugged it into Plancherel, you would violate it. Simple as that. And as I said, an interesting question is whether this estimate can hold in a non-field setting. In the case of Gauss sums, if n is not prime, one can show by a straightforward calculation that the square root law does not hold. But I thought it's worth taking a very quick aside to mention what happens in wider generality. Okay? Any questions so far? Life is good? Okay. All right. So this is a theorem. This is joint work with Brendan Murphy and Jonathan Patyanathan from 2014. So suppose you have a sequence of finite rings. Okay. Technically, if I want to avoid exceptions, which I do, of odd size. So the size of the rings is odd. So you have rings of odd size, of size going to infinity. And suppose that the square root law is satisfied, namely the summation over uv equals 1. So this is a Fourier transform of a hyperbola. Is bounded by a constant times the size of the ring of units raised to the power of 1/2. Okay? Then these rings are eventually finite fields. And these rings are not even required to be commutative. Okay? In other words, what this says, roughly speaking, is that the square root law is impossible in the non-commutative setting. Okay? And recently, my PhD student, Nathaniel Kingsbury, proved that if you take, if f is a polynomial in z of x1 through xd minus 1, and you look at the solution to the equation xd equals f of x1 through xd minus 1 over a finite ring R, then once again, if you have a sequence of these rings of size going to infinity, and the Fourier transform satisfies square root law cancellation, then for all but finitely many rings, exceptional rings, or matrix rings of small dimension relative to D, these are eventually fields. Okay? Here there are exceptions, but it's a small, finite list of exceptions. Okay? Once again, the theme here is that square root law, up to some small number of exceptions, is not possible in the non-commutative. It is impossible in the setting where zero divisors are allowed.
Do you know what happens, like, for arbitrary rings, you only get, you don't get anything, or do you get something in the middle?
So yes, you can get a lot of stuff in the middle, and exactly what you can get is a difficult question even in concrete cases, especially in non-commutative setting where it becomes an unholy nightmare, although maybe I'm just saying this because I'm not an algebraist.
So, and a typically interesting case is matrix rings.
Right. So from algebraic standpoint, matrix rings are very interesting, and there even the simplest examples are hard. Okay. Even the most elementary examples are hard.
2 by 2?
2 by 2 we can do, but the moment you start, yeah, well, this is precisely what Nathaniel was investigating. Okay, so going back to the problem at hand, I actually wrote down the proof of the Fourier inversion. So it is proved exactly in the way you think it does. You write down the definition and the proof writes itself. You just have to not interfere with the proof writing itself. And so using orthogonality of characters, you simply write down the definition, plug it in, and get the Fourier inversion formula. Okay, by orthogonality.
Can I actually also try something on your computer?
Yes, please. Absolutely. Zane already lowered my blood pressure. Maybe you can lower it further.
I wonder if it's stuck on continuous scroll.
Yeah, that's what I was thinking.
So it just needs to be stuck on a single page view.
I have no idea what you just said, but if it can be fixed, I'll be very happy.
Yeah, and then single page. Yeah, and then full screen. And then yeah, okay.
All right, so now Plancherel is exactly the same thing. As I mentioned before, if you have a sum and you square it, you just have to write it twice with different variables. I think this time I even managed to put the conjugation bar in the right function. I usually, it's a 50-50-90 rule, right? Okay. And the rest of the proof is again writes itself by orthogonality of characters. Okay, so this is Plancherel in Z and D. And now, before I dive into the sort of the classical theory of exact signal recovery, let me once again give you an elementary perspective, even though I sort of already did that in the continuous setting in the very beginning of this talk. Okay? So suppose that E in Z and D, and because if you have not seen signal recovery before, if you've seen it before, then all of this is natural and normal. But if you have not seen it before, it seems like magic. And I want to convince you that this is not magic, that it works, and then we'll go to more sophisticated methods. Okay, so E is in Z and D, and f of x is an indicator function of a set, so this is a binary signal, right? And suppose that the Fourier transform is transmitted, and once again, frequencies in S are unobserved. Okay? So by Fourier inversion, we can write the indicator function as the inverse Fourier transform of its Fourier transform. Okay, that's great. So then we can write it as a sum over frequencies that are not missing, plus the sum over the frequencies that are missing. I'm writing out exactly the same procedure as I did before, but actually this is going to come into play in a slightly more sophisticated form in later lectures, so I really do want to hammer this message heavily. Okay? So once again, we take the second term over the missing frequencies and we estimate it. And this time, I'm not even going to apply Holder, I'm going to apply the most important, no, I'm not even going to apply Cauchy-Schwarz. I'll apply the triangle inequality, and then the second term is bounded by n to the minus d over 2, times the number of terms, which is the size of S, times n to the minus d over 2, times the size of E, and we get n to the minus d times the size of E times the size of S. Okay? So suppose that this quantity is less than a half. We have seen this movie before. Okay? Then we can simply take the first term, which is the sum over the known frequencies, compute its modulus, and round up to 1 or down to 0. And then we have so we call it the direct rounding algorithm. By the way, essentially everything that's new that I'm going to talk about in these lectures is joint work with Azita Mayeli from City University of New York. And we call this direct rounding algorithm, but we didn't think for a moment that this is new. I'm sure that this was known when dinosaurs still walked the earth. Okay? And the condition that we get is that the size of E times the size of S is less than n to the d over 2. Okay? Which is exactly the condition that I promised in general, but in the general case, we'll have to use a different method. Okay? So what happens if we consider general signals? Okay? And this brings us to a very amusing historical point. So what I called it is Matolcsi and Szuchs, Donoho Stark point of view. So Donoho and Stark wrote a beautiful seminal paper in 1989 on this topic, but it turns out that some of the results were published in 1973 by Matolcsi and Szuchs. It was a paper published in the French language. In America, we don't like foreign languages, so nobody read it. But it turns out that what I'm going to describe now is already contained in the paper by Matolcsi and Szuchs in the setting of general locally compact abelian groups. Okay, so you have again a signal from Z and D to C. So the classical uncertainty principle, and I'm going to prove it later, even though it's very simple, says that the size of the support of H times the size of the support of the Fourier transform of H is bigger than or equal to n to the d. Okay? So then suppose that, by the way, another thing that I tried to pin down, and this was a waste of time because it's impossible, is when exactly this form of the Fourier uncertainty was proven. And I eventually realized that there was a paper by Boni from 1793, which essentially contained it. And I stopped there because I was worried that I would go into ancient Greece eventually. So anyway. So in other words, Heisenberg uncertainty principle was proved long before Heisenberg, at least in the mathematical. Okay. So suppose that F is a signal supported in E with frequencies in S unobserved, right? So what does it mean that F cannot be recovered uniquely? What it means is that there exists another signal G which has support of the same size such that the Fourier transform of F and the Fourier transform of G agree except for M in S. And F is not identically equal to G. So this is what it would mean if we could not recover F uniquely. Okay, so once again, you have missing frequencies in S, and we're trying to see what terrible things would happen to us if we could not recover it uniquely, and we expressed it in a mathematical language by saying that there is a signal G with the support of the same size, not necessarily the same support, but support of this because that's extra information. Okay, this is something that we'll discuss later. And the Fourier transforms agree away from this. Okay? So what do? we solve this problem the way all the problems in first year graduate analysis are solved, namely you take f minus g. Okay, half of them, fine. You take h equals f minus g. So it's clear that the Fourier transform of h is contained in S, so its size is at most the size of S. And what is the support of h? Well, it's f minus g. So its support has at most the size twice the size of the support of f, because if both f and g are 0, we're out of luck. Okay? And then we apply the uncertainty principle. And by the uncertainty principle, we must have that the size of the support of f times the size of the missing frequencies is bigger than or equal to n to the d over 2. So we just contradict that condition by assuming the opposite. And then h must be 0, which, and hence the recovery is unique. One of the things that I chose not to focus on in these lectures is the actual recovery mechanism. This is a very interesting issue. If you just want to convince yourself that some recovery mechanism exists, even if it's not very efficient, then the method of least squares will do it. You just consider all functions with support of that size, and then you solve the minimization problem.
But why not choose just to write 1, not 2, but 1, and round it? Because it's not...
It's a general signal.
It's a general signal.
No, for binary signals, there are no tricks needed. And moreover, the algorithm for binary signals is extremely fast. Even in practice, I coded it, and even in my laptop, it runs very fast. All right. So this gives us unique recovery under the assumption that the size of the support of f times the support of s is less than n to the d over 2.
So you said that the algorithmic problem is difficult?
I'm sorry?
So you said that doing this algorithm is difficult, or is not known how to do it?
There are many algorithms. But they tend not to be very good in practice unless you start making extra assumptions, which in practice you can make, but theoretically. In other words, if you're willing to accept that your algorithm is going to work, say, 99% of the time, you can speed up the algorithm enormously, okay, just by using random techniques. But as far as algorithms that are guaranteed to produce an outcome, there are many, and from a coding perspective, because I like programming, so just for fun, I tried to code as many of them as I could, and my computer kept exploding. So for example, the algorithm that I described can hardly be called an algorithm, it's exponential time. Right? So this is where if you talk to people in industry, they just walk out of the room. All right. Okay. So here we arrive at a question that was asked earlier about the sharpness of the uncertainty principle. So suppose that R is an odd prime. It doesn't need to be. There are examples in any setting, but this is just somehow simpler. And S is a k-dimensional subspace of Z and D. And let's say that k is at least 1, at most d minus 1 for simplicity. Then the Fourier transform is exactly n to the minus d over 2 plus k times the indicator function of the orthogonal subspace. Okay? And this shows that, so since the size of S times the size of S per is n to the d, the classical uncertainty principle is sharp. In fact, I'm not going to go into that, but one can show that all the sharpness examples, all the examples that are exactly sharp are subgroups. What is much less clear is what near extremizers look like. Okay? And this is one of the issues that I'm going to address, but very indirectly. You'll see what I mean. And one of the things that we're going to see is in the presence of non-trivial restriction estimates, of any non-trivial restriction estimate, we can do much better. And we are also going to see that non-trivial restriction estimates typically hold. In other words, it is extremely difficult. You're much more likely, if you look at Z and D, and you choose a subset of a particular size, you're much more likely to get hit by lightning twice or even 3 times than pick out a subset that does not satisfy a good restriction estimate. Of course, what I'm saying is an asymptotic statement, so it should be taken with the necessary grain of salt. Okay? Okay, this is cool. All right, so let's prove the classical uncertainty principle. It's very simple, but why not for the sake of completeness? So we write a function as an inverse Fourier transform of its Fourier transform, except that we immediately plug in the assumption that the Fourier transform is supported in S. Okay? Then, by the triangle inequality, one can use Cauchy-Schwarz and arrive at the same conclusion, but I just got bored using Cauchy-Schwarz all the time. So just the modulus of h of x is bounded by n to the minus d over 2 times the number of terms, and here the trivial estimate on the Fourier transform of h, which is n to the minus d over 2 times the L1 norm. Okay? So here I'm committing a small crime, a pedagogical crime. If my co-author was here, I would be in trouble, and that is I use x as a variable on the left-hand side and as a dummy variable on the right-hand side. If you do this when you teach calculus in the US, your evaluation drops immediately by a point. Okay, and so summing both sides over x and e and canceling the L1 norms, you get the size of e times the size of s is bigger than or equal to n to the d. If you applied Cauchy-Schwarz instead of the triangle inequality, you would be canceling L2 norms. Okay, and once again, everything works because if the L2 norm is 0, then the function is 0, because we're in the discrete side. And this is the classical uncertainty principle. And once again, I mentioned this a few minutes ago, but let me say it again, that the theme is that almost always, in a sense that can be made precise, the uncertainty principle is much better than this. And in particular, and we already saw glimpses of this, in the presence of any non-trivial restriction estimate on the LP scale, it's actually quite important that this is also true on the Orlitz scale, but more on that later. But if you have any non-trivial restriction estimate when p is bigger than 1, you obtain a better result. Now there's one thing that's very important to keep in mind, is that we're in a finite setting. And in the finite setting, more or less all estimates are true. The question is, what are the constants, right? So when I say that a better than trivial restriction estimate holds, what I mean is that the constant is something like 5, and n is like the size of the American national debt. Okay? Okay, so let me also state the additive energy uncertainty principle.
Does it mean you want independent of n estimates?
Whenever possible. Whenever possible, yes. Absolutely. So here's a version of the additive energy uncertainty principle. And so here I should mention in passing, so there's an experiment that I've been conducting in recent years, and that is getting strong undergrads involved, not just in sort of undergraduate research activity, but in real research. And this can definitely be done, provided that it doesn't require a lot of background. So here's a result that was actually proved this summer with several students. So this is Karam Aldale, that's my oldest son, Jamago, Azita Mayeli, and Svetlana Beck. And so here's the results. So suppose that A is in Z and D. So first define the additive energy of the set. A is the usual thing, the number of additive quadruplets. Okay? Because what are we trying to get at? We're trying to get at the idea that typically the uncertainty principle can be improved. There are many ways of framing this. Okay? And the way the result you're about to see frames this issue is that if this energy satisfies better than a trivial bound, then you get a better uncertainty principle. Okay? And so this quantity measures the extent to which a given set is arithmetically closed, right? And let me just make another trivial remark. If the set A is chosen randomly, in any reasonable sense, there's no reason to expect for this equality to hold, and the set is not too big, then there's no reason to expect for this equality to hold except in trivial cases. Okay? So here's the one form. I'm going to give you a couple of variants of the additive energy uncertainty principle. Suppose you have a signal with support in E, and the Fourier transform is supported in S. Then for any alpha in 0, 1, the following holds. You have the size of E times the maximum over all the subsets of S of the additive energy of U divided by the size of U squared to the power of alpha. And here you have the same quantity involving S to the power of 1 minus alpha is bigger than or equal to n to the d. Okay? So why is this a generalization of the uncertainty principle? I guess that's clear. Because the additive energy is at most the size of Q, so this maximum is at most the size of S, and we simply recover the classical uncertainty principle. Okay? One obvious criticism of this from a practical standpoint is how are you going to compute the maximum over the subsets of lambda u over the size of u squared? This is, of course, not a simple calculation, but there are some examples where you can do that. So for example, if n is a prime and the dimension is 2, then the unit circle satisfies this property, because in Zn2, if n is prime, just like in Euclidean space, the only way x plus y equals x prime plus y prime can hold is if x equals x prime, y equals y prime, or a permutation. Okay, and the antipodal case, of course. Okay, actually, we're going to encounter this later.
By the way, am I missing something, or isn't it the case that actually the alpha equal to 0 and alpha equal to 1 are actually everything, and the rest is just taking the geometric mean of this?
That's right. That's right. I should have commented that. You're absolutely right. Okay, so this is just what I described. And so this is the case of the circle that I mentioned. So here, the only way the equation is satisfied is if one of these three obvious cases hold. So in this case, the maximum of lambda of u over the size of u squared is 3. Okay? And so it follows that if f is supported in E, and the Fourier transform is supported in S in this setting, then the additive energy uncertainty principle tells us that the size of E is in fact bigger than or equal to n squared over 3. So it's a clear positive proportion of the whole space. This is something that we're going to see in different variations later on. Since n is prime, there are more algebraic ways of addressing the uncertainty in this setting, as we're eventually going to see. So there's a very beautiful version of the uncertainty principle in prime fields in Z mod P due to Terry Tao that I'm going to describe later. So he proved that if a function is supported in E and the Fourier transform is supported in S, then the size of E plus the size of S has to be bigger than or equal to p plus 1. And the proof follows very quickly from a theorem from 1924 by Chebotarev, which says that if you take a Fourier matrix in the prime case, then any k by k minor submatrix has a non-zero determinant. It's a really, really gorgeous result. Okay, going. All right, so restriction theory enters the picture. So what do we mean by a restriction estimate in this setting, in the setting of Z and D? So on the left-hand side, we take the Fourier transform of a signal, and we restrict it to the set S, and we divide by the size of S, and then other ways we take the LQ norm. So this is the weighted LQ norm, and this is bounded by a constant times n to the power of minus d over 2 times an unweighted LP norm on the right-hand side, okay? And as we discussed before, for this to be meaningful, you want CPQ to be some fixed constant, like, let's say no more than 10, and N to be very, very large, okay? And here is a result that's proven quite helpful. So this is once again joint work with Azita Mayeli. So if F maps Z and D to C, and S is a subset of Z and D, then the following holds. So notice that over here we have a constant, and then n to the minus d over 2. So n to the minus d over 2 is always present, and then you have the LP norm. So here, the constant is written out explicitly. So for any set S, the following result holds, namely that the L2 norm of the Fourier transform restricted to S, normalized, is bounded by the size of S to the n to the d over 2 to the power of minus a half, times the maximum over all the subsets of lambda u over the size of u squared to the power of a quarter, and then you have n to the minus d over 2, the L4 thirds norm. So we call it a universal restriction theorem, is because no assumptions are made, well, except that the constant, okay, nobody said that the constant is obligated to be small, but nevertheless, it holds for any set S. Okay,
So it definitely reminds hypercontractivity. I said definitely reminds hypercontractivity.
it does, and to be honest, it didn't occur to me until this moment. That's a good, maybe this should be looked into more closely. Okay? Does this make sense? So I always worry about the audience getting lost in the forest of symbols. This makes sense? So we have a restriction estimate, except that the constant is written out in the explicit form, and the additive energy is built into this constant, which makes sense. Okay. All right, so before proving the universal restriction theorem, we're going to develop a simple mechanism for going directly from restriction to uncertainty, where the more non-trivial the restriction estimate becomes, the better uncertainty principle we obtain. Okay? All right, so here's a theorem. This is last year, during work with Azita Mayeli. Suppose that F and F hat are signals where F is supported in E and the Fourier transform is supported in S. Suppose that S satisfies the PQ restriction estimate with norm CPQ. Okay? Then we have the following uncertainty principle. The size of E to the power of 1 over P times the size of S bigger than or equal to n to the d over CPQ. Okay? Now, remember I mentioned that when p equals 1, the restriction estimate always holds. Maybe this is worth amplifying. So, if you take the left-hand side and simply apply the triangle inequality, then it is bounded by the right-hand side when p equals 1. Okay, just like it is in the continuous case. So going back here, if p is 1, then CPQ is 1, and we get the classical uncertainty principle. But if p is bigger than 1, and this constant CPQ is under control and n is huge, then we get an improvement on the uncertainty principle. The case that is very interesting but highly technical, and I have not yet decided whether it's going to make its way into later lectures, is what happens if you work near L1, so some space like L1 log alpha L. Then one can derive a variant of this, and it's not rocket science, but it is a mess. Okay, I mean, just a technical mess. You know in advance, it's one of these most annoying things in mathematics where you know in advance that everything is going to work out, but you still have to bleed for a few days. Yeah. Well, a few hours in this case.
It's supposed to be symmetric.
Well, it would be if we made assumptions on E. The reason, this is essentially an arbitrary choice. You can make assumptions on E. The reason I typically, when I present these, make an assumption on S is the following, is I think of E as being a property of the message that you send. And you don't have much control over that. And I think of S as quite often being something random. So it is more reasonable from a practical standpoint to put assumptions on S than it does on E, because E is a property of your message. But this is arguable. But you're absolutely right. If you do make this assumption, you can run everything in reverse because Fourier transform for all practical purposes is an order 2 operation, even though it's not. Okay. All right. So now let's prove uncertainty via restriction. I'm going to prove a couple of versions. The second one is going to be in most cases better than the first one. Nevertheless, the first one has some value, as I'll explain later in these lectures. Also, it has a particularly simple proof. So once again, you write the function as an inverse Fourier transform of its Fourier transform. And you can restrict frequencies to S by the assumption that the Fourier transform is supported on S. Okay? Again, we apply Holder's inequality. So the modulus of f of x is bounded by n to the minus d over 2, size of S, times the normalized LQ norm of the Fourier transform restricted to S. Okay? So it's the same calculation we've seen several times already. By the restriction bound assumption, this is bounded by the size of S, the constant CPQ. This should be n to the minus d over 2. I tried to fish out every instance of using the old normalization, but clearly I didn't get them all. Okay, my apologies. And wait, no, this is right. Because this n to the minus d over 2 comes from the normalization. Another n to the minus d over 2 comes from the definition of the restriction estimate. Okay. Maybe I did get them all. We'll see. See, where am I? Yeah, so this is correct. Okay, and now by the support assumption, this quantity is equal to the size of S times CPQ times n to the minus d over 2, and the LP norm can be restricted to E because we are assuming that F is supported in E. And by the way, most, if not all, the results I'm going to present still work if you don't assume that the function is supported in E, but merely concentrated in E. But these are technical elaborations, okay, which I'm going to comment on in some cases, but not in all. All right, putting everything together, we see that modulus of f of x is bounded by the size of S, CPQ, n to the minus d times the LP norm over x and E. And now we simply raise both sides to the power of p. We sum in x, that introduces the size of E on the left-hand side. Then we take the pth roots and we get the size of E to the 1 over p times the size of S is bigger than or equal to n to the d over CPQ. Okay? I have 15 minutes, correct? Is that the, or when is it?
It was until 3.
Until 3. Oh,
Okay, we can.
oh no problem, no problem.
There's a short break before, we just need 5 minutes before the next talk, which is at 3:15. So.
No, but since I put all of everything on the same set of slides, this is great, and this is in fact a very convenient stopping point, so let me go ahead and stop there. Yeah.